A graduate student conducted an experiment in which 20 10-month-old babies were asked to watch a climber character attempt to ascend a hill. On 2 occasions, the baby witnessed the character fail to make the climb. On the 3rd attempt, the baby witnessed either a helper toy push the character up the hill or a hinderer toy prevent the character from making the ascent. The helper and hinder toys were shown to each baby in a random fashion for the fixed amount of time. The baby was then placed in front of each toy and allowed to choose which toy he or she wished to play with. 17 of the 20 cases, the baby chose the helper toy, complete parts A through D. Sort of a famous study here. I might show you a quick little video or image here within the video. Why is it important to randomly expose the helper or hinder toy first? Well, it's all about avoiding bias, right? So let's see what our choices here are. And what was this first one? Randomness in order to expose your infants to avoid bias. Maybe children generally like the first one they see, or maybe the researchers do something different with the helper toy versus the hinder toy. So we got to be careful with that. Okay, let's keep on going. So what would be the appropriate null and alternative hypothesis if the researcher is attempting to show that babies prefer the helper over the hinder? So we would expect what? That if there's no preference, that half. So that would equal point, and they already have 0.5 here, so that would equals 0.5. And so they're expecting that more than half. Now they have to set this before they even do the study. That more than half are going to prefer the helper toy versus the hinderer toy. Now, use the binomial probability formula to determine the p-value for this test. So we're going to go ahead and use a calculator here. So we're going to go to Stat, Calculators, Binomial. We've done this before in a much earlier lesson. Put in the total n is 20, p is 0.5, and we're wanting greater than or equal to 17. Make sure I got that right. 17 of 20 cases. Very unlikely. So I got 0.0001 right there. Looks like I put one too many zeros there. I thought it looked a little too small. There we go. So that's sort of like an exact p-value from this, not using the normal distribution to make an approximation. So what is the correct decision regarding HO? This is very small. It's very unlikely to get a proportion this large, right? Very unlikely to get a proportion that large. We're expecting to get half. If we're going to get 10, we wouldn't be too out of line if we got 11 or 12, but to get 17, that's very unlikely to happen by chance. It can happen, 1 out of every 1,000 times would that happen, but we're going to say it's probably not one of those. More than likely, they actually do prefer. So we're going to reject HO. There is evidence to suggest the proportion of babies who choose the helper toy is greater than 0.5. That's sort of hopefully just makes sense at this level. 17 out of 20, that's definitely way more than half. So in testing 11 6-month-old babies, all 11 preferred the helper toy. And they went ahead and gave you the p-value here at 0.12300005. Interpret this result. Okay, so what is this? This is 5 10,000ths times. So if I were to do this again, if I did this 10,000 times, only 5 times in 10,000s about would we see a result this extreme. So let's see which one of these does that. Well, it's definitely not exactly 5 or exactly 11, about 5. Where's this one right here? So the population proportion of babies who choose the helper is 0.5. A sample where 11 babies chose the helper toy will occur in 5 out of the 10,000 samples of 11 babies. So very unlikely to occur. It can occur, but very unlikely. And that's why we end up rejecting HO. So I hope that helps. This is a much more difficult question because we actually went back to using to find the exact p-value using binomial.